Look, we all see it. AI models are getting powerful, frighteningly powerful. But as they start to think in more abstract ways, we're running up against a really fundamental question. Can we actually guarantee they're safe? And what are the hard limits to doing that? That's what we're going to unpack today. And this quote, well, it just hits the nail on the head, doesn't it? The problem isn't that it's getting a little harder to check our work. The gap between what an AI can do and what we can prove about its safety is blowing up. It's growing exponentially.
So, where does this all start? Well, it begins with how these models are evolving. They're not just getting faster at old tricks, they're fundamentally changing how they think. They're climbing up what you could call an abstraction ladder.
Okay, let's make this real for a second. An older model might just compare two things directly, right? Like, do these pants go with this shirt? But something like the OutfitTransformer we're seeing now, it does what's called a structural ascent. It understands the entire outfit as a whole concept. That's a huge leap in thinking. It has climbed the abstraction ladder.
Right. So if these models are operating on a whole new level, our safety methods have got to catch up. And that's where this idea from the research comes in, a framework they call Post-Abstractive Safety. It's designed specifically for this new kind of risk.
Post-Abstractive Safety, or PAS, is basically a theoretical ceiling. Think of it this way. You keep adding more and more abstract safety rules. At some point, you hit a wall where adding another, even more abstract rule doesn't actually make the system any safer. You've saturated the guarantee. That point of no return is what's called the greatest fixed point.
So how do you actually find that point? Well, you start with the absolute strongest, most comprehensive safety rule you can imagine. We call that top. Then you start applying these abstraction operators, one after another. Each step refines the safety rules, creating this descending chain of checks. But here's the thing, that chain can't just go down forever.
And here's why it has to stop. It's baked into the math. In this kind of formal system, any strictly descending chain is bounded. It has a finite length, determined by that initial top predicate. So the process has to stabilize at some point. It has to land on a fixed point, what we're calling kappa. It's not a maybe, it's a logical certainty.
Okay, this is where it gets really fascinating. We've talked about model power and we've talked about safety analysis. But what's the actual connection between them? How does a model's raw horsepower relate to how hard it is to verify its safety?
This is it. This is the core connection, called the capacity-depth theorem. In simple terms, it says the depth of your safety analysis, how many of those descending steps you need, has to be at least as big as the model's capacity. And we measure that capacity with something called the VC dimension, which is just a fancy way of saying how complex are the patterns this thing can even learn. The bottom line? More power demands more safety depth. Period.
And the takeaway here is huge. It means as we build more powerful models, we don't just choose to do more complex safety checks, we are mathematically forced to. A model's expressive power and the complexity of its safety verification are completely inseparable. They're tied at the hip.
So there's a direct link. That's one thing. But the cost of that link, that's where we slam into a massive, massive wall. Because the relationship isn't nice and clean. It's much, much worse.
It really comes down to this question, doesn't it? If we need to add just one more level to our safety analysis, what does that actually cost us in terms of the model's resources?
This table just lays it all out, and it is brutal. You see, if growth were linear, adding one more level of safety might cost you, say, 10 more units of something. But we don't live in a linear world. We live in a superlinear one. And here, adding one more level of safety means you have to multiply your resources by 10. The cost just explodes.
For any ML engineers watching, think about it like this. Your safety framework is a building. To add one more floor of safety guarantees, you can't just plop some more bricks on top. No, you have to go all the way down to the bottom and rebuild the entire foundation to be exponentially larger just to support that one extra floor. That's the brutal cost of superlinear separation.
And this isn't just a handy analogy. The math proves it. This formula shows that to get that deeper safety, the number of parameters you need in your model, its width, its depth, you name it, just blows up exponentially. This resource explosion isn't a bug. It's the unavoidable price you pay for deeper safety.
So we have this exponential cost wall. But you know what? Even if we had infinite resources, even if we could pay that cost, we'd still run into one final barrier. And this isn't a limit of engineering, it's a limit of pure logic.
And there it is, Rice's theorem. It's a classic in computer science. And what it says is that for any system powerful enough to be Turing complete,
and our big models are, it is literally impossible to write a program that can prove all interesting things about it. And is it safe is a very interesting question. The problem is fundamentally undecidable. You just can't do it.
Well, that kind of changes things, huh? If that gold standard of a perfect mathematical proof is completely off the table for our most advanced AIs, then what on earth are we supposed to do?
This is where we have to shift our entire goal. We have to move away from this idea of absolute, formal proof, which we now know as a dead end, and move towards empirical validation. We have to aim for overwhelming evidence instead of impossible certainty. And look, this isn't settling for second best. It's the only practical, intellectually honest path we have.
So what does that look like? Well, it means we start running smart experiments. We can build tasks with different levels of abstraction and see how a model's resource needs change. We're basically hunting for a structural witness in the data, a specific curve where the cost of accuracy shoots up superlinearly. If we find that curve, it's a huge piece of evidence that this entire theory is right.
And let's bring this right back to where we started. This isn't some sci-fi thought experiment for the future. Models like OutfitTransformer, with their massive need to understand complex relationships, are the reason this is so urgent. These superlinear costs and these verification limits, they are the very real engineering problems we are dealing with today because of how powerful our models have become.
Which leaves us with this final, frankly unsettling question. If the case laid out here is correct, that our most powerful creations are, at their core, beyond our ability to formally verify, how should that change how we decide what to build? It's not just a technical question anymore. It's a question of what we should even be aiming for in the first place.